All right, this is the beginning of the lesson on graphing sine and cosine functions that have period changes and phase shifts. So, we've learned about amplitude, midline, and the period of the sine and cosine functions, the parent functions, y equals sine of x and y equals cosine of x being 2 pi radians. So now we're going to look at problems where we have a horizontal translation, which in trigonometry we call a phase shift, and that moves our functions to the left or to the right a certain number of units. And if there is no horizontal translation, we say the phase shift is 0 radians. We're also going to look at graphing sine and cosine functions with a horizontal stretch or compression. And that means that the period of 2 pi will change to something other than 2 pi radians. And then we could still have a change in the amplitude with a vertical stretch or compression. We could still have a vertical translation, which would change our midline to something other than y equals 0. And we could still have a reflection across the x-axis as well, which would change maximums into minimums and minimums into maximums. So one of the things we need to understand is the structure of our sine and cosine functions for calculating the period and the phase shift. So here we can see, so what we're looking at when we calculate the period of a sine or cosine function, we've talked about this before as well, but today it's definitely going to be something other than 2 pi. So our 1 over b parameter will be something other than 1. So that's our coefficient of x, and we take 2 pi divided by the positive value of that, and that then will give us the period. The phase shift is calculated by taking the value we call c, which means we'll have to take the opposite of this quantity that we find here, because you'll notice it's minus c structure, and we want c structure, which is its opposite. We divide that by the 1 over b parameter, positive or negative, whichever it would be, and then that becomes our phase shift. If the phase shift is negative, that means that we have a translation to the left, and if the phase shift is positive, we have a translation to the right. All right, let's take a look at this problem. We have g of x equals negative 3 cosine of x divided by 3. First thing we're going to do is calculate the period, amplitude, midline, and phase shift. So the period would be 2 pi divided by 1 over b with a positive value. So we have to be able to remember, see this structure as negative 3 times the cosine of 1/3 times x. So we know then that negative 3 is our a parameter, and the 1/3 is our 1 over b parameter. So we have our 2 pi divided by that 1 over b parameter of 1/3, which would be 2 pi times its reciprocal of 3, which gives us a period of 6 pi radians. The amplitude, remember, is the absolute value of our a parameter, so we have an amplitude of 3 units. And it's a good thing, I would say, to note here, so that we don't forget, though, when we graph, we are still going to have to graph an x-axis reflection, which is going to turn the maximums of the parent function into minimums and minimums into maximums. Midline. Midline, remember, is y equals k. The structure of our function shows us that our k value is 0. So this would be like a minus 0 in parentheses. That's actually going to give us our c concept here, plus 0. So this is our k parameter. So we have y equals 0. And then our phase shift, we take the opposite of this value to get what we call c. Well, the opposite of negative 0 or the opposite of 0 is 0. So we get 0. We divide it by our 1 over b. 0 divided by any other number is 0. So we have 0 radians as our phase shift, which basically means we don't have a phase shift. So this function does not move to the left or to the right compared to its parent. All right, so now graphing. Looking at a scale. So I would take and look at the period, which is 6 pi. So I have a possible scale that I can use nicely here. Would be my period of 6 pi radians divided by 4. And reducing that, we get 3 pi halves, so it's 1.5 pi as a scale. That's a little large for me. I could also use a factor of that, such as pi halves. I kind of like the pi halves. And I have 26 squares here, so that will allow me to get 6 pi, which is a full period, so that should give me a decent graph of this function as well. And so now my axes. So I have no vertical shift. My midline is the x-axis. I have an amplitude of 3, so that's pretty easy to do. So I'm going to put my x-axis in the middle of my graph here. And as I mentioned, if with no phase shift to the left, if I want to graph most of my function to be positive, I would push my y-axis to the left. And then using my scale of pi halves, every 2 squares is going to be pi. So this will be pi, and a 2 pi, 3 pi, and so on. And for my y-axis, I'm just going to use a scale of 1 unit. And then, so now I have to realize, okay, I'm graphing a cosine function. We know cosine starts its first cycle at 0, 1. And so we have to transform this point based on our a parameter, which is the -3. So it stretches to 3 units above the x-axis and then reflects below it to 0, -3. That's the beginning of this function's first cycle. We know the period is 6 pi, so 6 pi radians later, we'll have a point with this same y value of -3. So from 0 to 6 pi would be 6 pi radians, so there I have another relative minimum. So these are both going to be relative minimums. What we need to understand about the cosine function is exactly halfway between 2 relative minimums, it will have a relative maximum. And my amplitude being 3, and my midline being my x-axis, it will be 3 units above y equals 0. We also need to understand for the cosine function, exactly halfway between a maximum and a minimum, we have a midline point, which in this case would also be an x-intercept. So that would put us here and here. Now I have a little bit more room over here to extend my curve. So another 3 squares over, I would have another midline point. But that's all I can fit based on my positioning of my y-axis rather, and my scale. So now I'm going to draw in my curve. So this is a relative minimum. Maximum. And then this one is a midline point, so it keeps heading up to its next maximum. Put my arrows on the end, and there's the graph of this function. All right, let's take a look at the next example. So here we're going to graph g of x equals sine of 2x minus 3. So calculating all of our key things here first. Structurally speaking, we have to see this. So we have an a value of 1. That minus 3 is not included with the 2x because there are no parentheses around it. So we have 2x minus 0 as that 1 over bx minus c structure. So the 1 is our a parameter. The 2 is our 1 over b parameter. The opposite of that minus 0 is again our c, and our -3 or minus 3 here, this is our k. All right, so the period of this function would be 2 pi divided by our 1 over b, which is 2. And in this case, that just reduces to pi. So we have a period of pi radians. The amplitude is the absolute value of the a parameter. Absolute value of 1 is 1, which is the period of the parent function, or the amplitude rather of the parent function. So that's actually the same. Midline is y equals k. So we have a -3. So this time, though, we have a vertical translation down 3 units. That's where our midline is going to be. And then phase shift. So phase shift, we take the opposite of that -0 again, which is 0, divided by the 1 over b parameter of 2. 0 divided by a new number is 0. So again, we have no phase shift. Quite honestly, in these first couple of examples, we're just focusing on functions that have a change in the period. That's what we're looking at here. All right. So now, possible scale. So my scale here that I would use would be pi-fourths, because if I take my calculated period of pi and divide it by 4, that's what I get. I like that. I like pi fourths. So I'm going to use pi fourths. And now I do have, remember, this midline at y equals -3 and an amplitude of 1. So I do have to make sure I can get down to -4. Other than that, there's not a whole lot to be concerned about. So I'm going to push my x-axis up a little bit. And my y-axis, again, I'm going to push to the left so I can graph mostly positive or to the right parts of my function, which is just a personal choice since I can do that here. And I'm going to use a y scale of 1 unit again. And my x scale, as we've talked about, is pi fourths radians. So every 4 squares is a multiple of pi, and every 2 squares is the half mark. So this is pi. Another 4 will take us to 2 pi, 3 pi, 4 pi. And then if you want to put in the halves, you can. And over here, this would be negative pi halves. All right, so now graphing my function. Here I'm graphing a sine function. Sine, we know, starts at 0, 0. So the only transformation that's going to affect that is our change in the midline. Oh, I want to graph my midline. I like to have my midline graphed when it's not my x-axis. So let me do that. So y equals -3. That's my midline. And so my 0, 0 moves down to the midline at 0, -3. Now I know the period is pi. So pi radians later, I'm going to have a point that's also on that midline. And that would be right here. That's the end of the first cycle. We need to know for sine that halfway between these two midline points, we have another midline point. And that third midline point in that middle is what's going to separate the maximum minimum sections. So now what I have, we have to know that from the first midline point for sine, it moves to a relative maximum. And our amplitude is 1. We have no x-axis reflection this time because our a value is positive, so it will remain a maximum, 1 unit above the midline. And then halfway between the next two intercepts or midline points, we will have a relative minimum. And then we extend that to cover the rest of our graph. And we can do a little bit on the negative side. Almost made it through it without it doing that. Doesn't like that spot. All right, so this is a midline point. It's heading up to its next maximum. And it's curving through. Nice and rounded at its maximums and minimums. And here I have another midline point, so it's also heading up to its next maximum in that case. And there is the graph of that function. All right, this will be the end of the first video that includes the first 2 examples. The next one will include the next couple of examples.